So let's go ahead and start. We're going to go ahead and do 7.2, which is sample proportions. So sample proportions, and then 7.3 is going to be sample mean. Okay, so it makes sense, right? You do a sample, you can do different ones, right? You can either do a sample on a categorical variable or a quantitative variable. So it's either going to be a proportion or a mean, right? So we're going to do proportion first, okay? So sample proportion. So let's go ahead and go to page 459. In the middle of 459, it says there's a definition there. The sampling distribution of the sample proportion p hat describes the distribution of values taken by the same proportion p hat in all possible samples of the same size from the same population. Okay, nothing new here, right? Okay, it's the same thing that we talked about before. Underneath there, there's an activity called the candy machine. Now, I'm not going to go through this over with you guys, but I highly recommend that you guys do this on your own. Okay, if you go to it, where is it? There's an applet on www. So this is on top of page 460. I'm reading off. It says number 1, launch the Reese's Pieces applet at www.rossmanchance.com applets. Okay, and do 1 through 7, and you'll find some interesting things there. Okay, okay. So that being said, and I'm going to assume that you're going to do this. Okay, I'm going to assume that you're going to do that. Right, but in the meantime, let's go to page 461. On the bottom, it says the sampling distribution of a sample proportion. Okay, so A, it says the first dot, it says, okay, choose an SRS size small n from a population of large n with a proportion of P of successes. Let P hat be the sample proportion of successes. Then, okay, so in other words, we have a population here. We're going to take a sample. So we have population of large n. We're going to take a sample of small n. Okay, this guy has a true proportion or proportion here, right? And the sampling proportion will be p hat. Okay, we already know that the mu of p hat is going to be equal to p. We already did that. We did the 0.5 when we looked at the 0.5 of the blue chips versus red chips, right? So that is the first one there. That is, so it says the mean of the sampling distribution p hat is p. You flip the page, the standard deviation. So the standard deviation here is going to be Sx, or the standard deviation of the p hat is going to be equal to p1 minus p over n quantity square rooted. Okay? Okay, now there's a proviso here. For you to use this, there's a proviso that says small n cannot be greater than 0.1 n, right? Okay. And we've seen this before. What did we call this? Where did we see this? Can anybody tell me where we saw this? We saw this in the binomial stuff, and we're doing binomial distribution, right? When, as long as n is less than 10%, okay, in other words, as long as you are not oversampling, okay, you can say what? We can say that the success and failure follow a binomial distribution, right? That's what this guy here was, okay? Then also, on the very bottom, it says if you meet large counts, okay, if the large counts is, so what is a large count? So large counts against was NP greater than 10, and 1 minus P was greater than 10, okay? And we saw this again when we were doing the binomial distribution. We said that if this was good, we said that the distribution now becomes a normal distribution, right? This was the threshold, or this was the what had to occur for you to be able to say it's a normal distribution, okay? Again, so the three things happening here, right? This guy here, okay? The mean of the p hats is the same as the true proportion of the population. That's number one, because it's an unbiased estimator, okay? Number two, we have the standard deviation of the sample proportion is going to be this guy, as long as you do not oversample. As long as this guy, if you do not undersample. Okay, that's number two. Number three, if the large counts are met, the large counts condition is met, you can say that the sampling distribution of the p hats is a normal distribution. Okay, all right. So that's basically where we're at. Those are the things that you need to know of this. Okay, let's go ahead and do a couple of examples. Let's do the backing the pack example. Let's do the backing the pack example. Okay, backing the pack. Suppose that 84% of students at a large high school regularly use a backpack to carry their books from class to class. Imagine taking a simple random sample of 100 students and calculating p hat, the proportion of the students in the sample who regularly use a backpack, okay? So I'm doing a sample size of 100. The population, the regular population, I do not know. Well, I only know that it's a large high school. Okay, it said it was a large high school. Okay. I know that the true proportion is 0.84. It told me that it was 0.84. Okay, I know that much. So A, identify the mean of the sampling distribution of p hat. So I want to know what the mean of the sampling distribution of p hat is, and it's going to be the same as this. So it's going to be 0.84 because it is an unbiased estimator. It's an unbiased estimator. Okay. That was A. B. Calculate and interpret the standard deviation of the sampling distribution of p hat. Verify that the 10% condition is met. Okay. So what we're saying is that we're going to assume that this large high school is like a 6A school in our class, in our school. So it would be what, like 2,000, right? So if it was like 2,000 or greater than that. So 10% would be 200. And so since we only sampled 100, we're going to say that it met the less than 10% rule there. Okay, and then we're going to have to calculate the standard deviation of p hat is going to be equal to p1 minus p over n square root. So I'm going to get what? 0.84, that's p. 1 minus p is going to be 0.16 divided by n, which is 100. And then I'm going to take the square root of that, right? And if I do that, I am going to get 0.0367. 0.0367. Okay, C. Describe the shape of the sampling distribution of P. Justify your answer. Okay. Because so what do we know? So it could be normal, right? We're hoping that it's normal. And what needs to be met for it to be normal? You have to have n p and n1 minus p both have to be greater than 10, right? So the n here is going to be 100. P is 0.84, so that's 84, which is definitely greater than 10. And over here, I'm going to have 100 times 0.16, which is 16, which again is greater than 10. Okay, since it meets the large counts condition, I can say that this is a normal distribution. Okay. All right, so that's good. So that was that one, and then let's flip the page. On page 464, let's look at that example there and see what we can find there. Page 464. A polling organization takes an SRS of 1,500 first-year college students, how far away their home is. Suppose that 35% of all first-year students attend college within 50 miles of home. Find the probability that the random sample of 1,500 students will give the result within 2 percentage points of the true value. 2 percentage point of the true value. Okay, all right. So the sample was 1,500. Okay, and we're going to assume that this is less than 10% of all the college freshmen in the U.S., right? Right. So yeah, so it's definitely we're going to say that it meets the 10% rule there, right? And we are going to say also know that so we found that it was 35%, so mu p hat was 0.35. Okay, so I know that this guy here is going to be 0.35 because it's an unbiased estimator, right? Okay, and then I want to find what is the, what am I trying to find? Okay, to try to find that is 2 percentage points within the true value. Okay, so let's go ahead and find the sigma. Sigma p hat is going to be equal to square root of 0.35, that's p. 1 minus p is 0.65, 1 minus that, over 1,500. If I do that, the book tells me that I get 0.0123. 0.0123. Okay, so that's my sigma. That's my sigma here. This is my mu. So that's a normal distribution, right? And so, well, why, let's verify that it's normal distribution. So I have to have NP, which is going to be 1,500 times 0.35, and that is definitely greater than 10. And 1 minus p is equal to 1,500 times 0.65, and that is also greater than 10. So it does meet the large counts. So I can say it's a normal distribution. So it's just going to, I'm going to have what? I'm going to go like this, I'm going to go like this, 0.35 with a sigma of 0.0123. Okay. I want to find what is the probability. Find the probability that the random sample of 1,500 will give a result within 2 percentage points of the true value. So this is the true value. Okay, I want to find the 2 percentage points within here, right? So it would be what? If I use the norm CDF, what am I looking at? I'm looking at norm CDF. I'm looking from 0.033 to 0.037. It's 2 percentage points from here, right? So I'm looking at this guy here. I'm trying to find this percentage here. So the lower bound is 0.33, upper bound is 0.37 with a mu of 0.35, standard deviation of 0.0123, right? So that's what I need to calculate on my calculator. And if I do that, what do I get? 0.8961. 0.8961. Okay, so everybody understand why I'm using the norm CDF, right? Because I was given a bound here, and I want to find the probability within the bound. Okay, and the bound was between 0.2%. So it'd be here and here with, this is when this is the sigma. That's why I'm using this sigma, this is the mu, lower bound, upper bound. Okay. All right, so we're good with that.